Hey, hello everyone. From now on we are going to start using all these online courses, and I found out a pretty nice writing drawing pad, and I'm going to using this software to do all the writings, so I don't have to scan all my hard copy notes to the website, and I think this is pretty helpful. So this will be the pointer of the mouse, and I have different options for the colors. So I think let's look at the course schedule first before we move forward to anywhere. Okay, so seems like we only have how many weeks left? 1, 2, 3, 4 weeks left before the final exam week. So definitely the final exam won't be happen at a regular classroom as escalating, outbreak. So I'm gonna be creative and find out a way to figure this out, but I'll let you know later. So this week we are going to deal with, I think I need to refresh it. Yeah, so I just added another lecture here. So I'm going to record the videos and submit the videos, make available link over here, just below the title of the course. So it will be available before this time point, which is the regular time for the lecture, every month, Monday, Wednesday, Friday. And it's flexible for you. You can watch it anytime you like, but you must submit the homework on time to me, right? Uh, I am not receiving hard copies. Do not mail them to me. All right, just take pictures, write on the paper, and take pictures. And if you want to buy a same pad, which is just do all these handwritings into an electronic version, which is great. But if you do not have which is fine, even though it's just $20. But you can also write on the paper. And so, what about the simulation though? I mean, the simulation becomes hard. Um, so feel free to put the simulation figures onto one page and take a picture of that on the computer monitor or whatever way you want to do. You can make a screenshot and combine the figures with your hard copy figure together. And finally, you can use PDF24, which is an open source PDF creator, which is free. So you can download this one to the computer and combine all these files into one PDF. Do not send 20 files to me at the same time, since it's pretty hard for me to reorganize all these pages into one and grade it. Okay, so we have 32 students in the class. Please only send me one single file. If you didn't do that, I will return it back to you and give you a 0 at that point. I will change the grade whenever I receive the one single file version. Okay, so I'm trying to keep the videos short, probably 20 minutes per video. It's not because I'm trying to shrink the contents of the lectures for every video. I'm just because during the regular class, I'm gonna have conversations with students, so it takes longer time. Over here, I just myself, right? So it will take a much shorter time to cover all the contents. If I do a 55 minutes video, it's going to be a lot of contents. Probably can cover 2 lectures or 3 lectures. There will be a lot of homework assignments for you guys. And before I'm boring you, right? So I want to just keep the videos short, about 20 minutes, 15 to 20 minutes, and um, that's it. So after this video, there's no homework assignments. But there will be 2 homework assignments after you watch the second video on the 1st of April. And we'll cover some of the current meters, probably the current meters 1 on Friday. And probably there are another 2 or 3 sessions for current meters. And then amplifiers and BGTs, and we're done for this entire semester. So not too many stuff left. But they are pretty useful and practical. So hopefully you can you can still learn this stuff before the end of semester, even though we have so many uncertainties going on. But I think this will work because the videos are videos. They will be available on YouTube. You can check them out whenever you are available. So now let's get back to the topic. So I'm going to use this software, do all the writings. All right. So let's do a quick review first. Okay. Remember what we covered previously. We have NMOS and PMOS as a CMOS for the integrated circuits. And if I, it's not right, it's too high. So if I'm drawing an NMOS and I'm trying to power it up here at the gate and power it up here as well. Here's VDS, here's VGS. There will be a current flow through the channel, and we call it IDS. Okay, and there are two regions for this NMOS to operate. If you draw a IV curve, so here is the VDS, and here is IDS, and it looks like this. Okay, and this region is called linear or child region. And this region is called pinch off or saturation region. Okay, and for the transistor working in the linear or child region, and there will be an equation to control the current flow through the channel. And that equation is IDS equals to KPN if it's the NMOS, and that's the width, that's the length, and VGS minus VTHN, and times VDS minus VDS square over 2. And you want to keep all these things in one parenthesis. So that's IDS in the linear or child region. Okay, and because the name is, we name it as a linear region because this region is pretty similar to a linear line. So linear means it has a constant slope, and the slope here, because this is delta what? Delta I, and that's delta V. So the slope is actually delta I over delta V, which is 1 over R. So if delta I over delta V is a constant, so 1 over R will be a constant, and R will be a constant as well. So it seems like it's working in the child region and it performs like a resistor. So this is how we treat this region. And because we know it works like a resistor, so can we get a resistance of this channel? So the answer is yes. Save it. That's page 1, and I will erase all. So because we have the equation for the linear, for the current, and so we know that 1 over the resistance of the channel equals to the derivative of ID over the derivative of VDS, which equals to what? KPN, the width over the length, and VGS minus VTH N minus VDS. Okay, And because that the VDS is tiny. So the reason VDS is tiny is because it's being operated in the linear region. Because the VDS is small, so it's operating in the linear region. And now it's in the linear region, so VDS is tiny. So what we can do is we can directly ignore VDS. Okay, you ignore VDS, and what's left is KPN like this. And because we use like some extra line here to get rid of that. We assume this is beta n, just use beta n to denote this part. So the entire thing equals to beta n VGS minus VTH. Okay, and remember this for now. So that's when the transistor is being operated in the linear region. Okay, so what about when it is being operated in the saturation region? Okay, we are getting IDS equals to beta n VGS minus VTH n square. Okay, and if we inject a small signal to the NMOS when it's being operated in this region, and for example, this value is 1 milliamps. Let's see what's the value I'm using here. Yeah, let's assume this one is a 1 milliamp. No, 1 millivolts sine wave signal, and this is 2 volts. This is 2 volts as well. And because this DC voltage is going to set up a let's redraw it since I didn't do a good job on that. So this DC voltage will set up the DC operating point for the NMOS. So that's why when you add a little AC voltage to the gate, and it's going to oscillate the voltage, and at the same time it's getting a gain for the current. So for example, this is the DC voltage 2 volts, and this range is a 1 millivolt range. And finally, this AC voltage will change the current output because it follows this IV curve, right? And this is IDS, which is a DC current. And now that will be the oscillation of ID, the AC ID signal. Okay? So the square law equation shouldn't be this anymore because this is only in the DC region. But now we have AC being added to this. So finally, we use this one, smaller I, but capitalized D and S to denote a combination of a DC signal and AC signal. So IDS equals to VGS, which is a DC, plus the small VGS minus VTHN square. Okay, and this equals to beta n over 2, and we can use a smaller v and capitalize the G and S to denote the combination of the DC and AC signal. Okay, and then we can find out the transconductance of this of IDS over VGS. So the way to do that is do a derivative of IDS over this, which is, because 2 will be moved, will be canceled, this 2 here. So there won't be any 2 anymore. So it's going to be beta n and VGS minus VTHN. Okay. So this term is called the transconductance of the NOs, and we use GM to represent it. Okay. So this is an important concept you need to know. So that's the transconductance. Okay. So based on that, we derived a few equations out of it. Okay. So we know that GM, we just derived it from the last page. So GM equals to beta n VGS minus VTHN. So keep in mind, because the small signal input is tiny, so VGS, and we assume that VGS, which is a combination of the DC and AC, is pretty close to VGS, the DC only. So that's why we can directly use this one to calculate the GM. And now if you compare this one to the R, so this is, we're talking about this one in the saturation region, right? And if you compare to this parameter we just calculated, what did I do? No, it saved me. So this one equals to beta n VGS minus VTHN as well. But this is in the linear region. It has a different VGS. So they are being operated in the different regions. They are using the same equations, but they are different parameters. Just keep in mind. And based on this, okay, since we know that IDS in the saturation region, IDS equals to beta n over 2 VGS minus VTHN. And from here, if we move 2 over to the left side, we are getting 2 IDS equals to beta n VGS minus VTHN. All right, and then if we times beta n on both sides of the equation, we are getting 2 IDS times beta n, okay, equals to beta n square and VGS minus VTHN square. And so if we do a square root on both sides, we are getting this. Which is exactly GM. Okay, GM. So this is an important equation you need to know as well. So that's another way to get GM when you know IDS. Okay, so these two equations are are pretty important. So it's page 4 now. Another one you need to know, because we know that ID, IDS equals to beta n VGS minus VTHN. And so if you convert, if you know IDS, you can directly get VGS. Okay, so the way to do that is move 2 to here, and so VGS minus VTHN equals to 2 IDS over beta n, and then do a square root on both sides, so VGS minus VTHN equals to this. I still need some time to train myself on writing on the pad IDS, but I think this is good. Plot. So if you move this over to the other side, you are getting this. Okay, if you know that, it's going to be pretty handy as well. So let's come back to the example we are trying to get through. Okay. So here is a DC operating point, and and there will be a little AC signal, which is 1 millivolt, and this is 2 volt, and you get another DC, which is 2 volts as well. So if I'm asking you to calculate what's ID, what are the steps to calculate for ID? Okay. So the first thing you need to know is, so the reason we want to calculate it for GM is because it's connecting the VGS to ID. So if we are only looking at AC ID, so ID actually equals to GM VGS. Keep in mind. So VGS is the AC VGS, which is 1 millivolts over here. And GM, you can calculate it using the VGS to get the saturation IDS flow through the channel. So after that, you should be able to get IDS. So the steps, let's look at step 1, which is you need to know GM equals to what? Beta n. And for example, this is 10 to 1 for width and length. Okay, so it's beta n times VGS minus VTHN. And this is, what is beta n? Beta n will be, it's 120 micro over, not over, so 10 over 1, and 2 volts minus 0.8 volts. And this equals to what? 100, so 1200 micro amps per V square, so which is a unit of the KPN. Yeah, if I don't include the units, I don't want to do that always. It's confusing you, so let's don't do that. Let's just keep the dimension there, which is 1200 micro, and this times 1.2, which will finally be times 1.2, and I know 12 times 1.2 times 1.2 will be 1.44. So this will finally be 1440 micro amps per volt. Okay, so that's GM. think I didn't make it right. Did I? So GM is 1 milliamps per volt. So did I make any mistakes somewhere? VGS is 2 volts. 2 volts minus 0.8 volts. Yeah, depends on threshold voltage. I don't think there's anything wrong. So it's right. So beta n equals to kpn times the width over the length, which is 120 microamps per volt, times this times 10, and then times this. It's going to be this. So that's step 1, right? And step 2, calculate ID equals to GM VGS, which is 1440 microamps per volt times VGS, which is 1 millivolt, equals to, are different. So this equals to what? Oh, it's tiny. 1440 nano amp. Okay, so that's ID. That's ID. The AC current flow back and forth in the channel. Okay, that's the way to calculate it. You can directly calculate GM by using this, or you can calculate ID first, and then you use this one to get GM. Either way, so you can get a GM from here, but you have to calculate IDS first. If you do not IDS, you can directly calculate GM by using this equation. Okay, so you're asking, so why do we need an ID? The reason is in a lot of amplifiers, they are going to connect the resistor on the drain at the drain terminal, and whenever you get the ID times the resistor, you are going to get the voltage output, and you can compare the voltage output to your input voltage and to find out AC voltage gain. So that's the final purpose, but we are not getting there yet. So let's look at another example. So we will be able to know why you want to find out ID. Mm. 5, save. Whoa, do I have 5? I think so. Oh, I have 5 already. Oh, it's already saved. Never mind. Erase all. So let's look at one example. And then I think we are pretty much done. And another example in the homework assignments, I'm going to show you how to do the simulation. And then we're done for this video. I don't want to make it too long. So here's the example. So if I make this thinner, probably I can write more stuff on each page. All right, so here it goes. I will draw AC signal first and a DC signal. I really don't like the drawing. Let me redraw it. Here's O. So AC, DC, NMOS, and resistor on the top. And here's 5 volts, 5K ohms resistor, and here's VL. And it is 10:1 ratio. And this is 1 millivolts. And this is 2 volts. Okay. And the question is, what is VL AC wise? Okay. So this is pretty interesting. This is a pretty standard example actually. When you are having a DC, it's a mixed signal like DC and AC, how you can deal with it. So the first step, it can be a little bit confusing. You are thinking about why we have to do that. It's so funny. It's been confusing people for a while. So the way to do that is when you are only dealing with AC signal, short all the DC voltages to the ground. Okay, so you want to model that one into this AC only. Why do I ground that? Because there's a DC voltage over here. I short it to the ground. So you want to ask why we can do that? Because of superposition. Because we know the AC signal is something like when you are working in the lab, you activate the AC coupling, right? If you do the AC coupling, it's only going to show you the AC signal, but not the DC offset. If you're doing a DC coupling, it's going to show you everything. Sometimes the signal is out of the monitor, it has a huge DC offset, and you do want to remove it before you can see anything in your signal, right? So it's the same concept. I just ground all these DC signals. I know the DC signals are not ground, but compared to the AC, they are being treated as an AC ground. This is a pretty interesting concept, and it's kind of virtual. You couldn't imagine why, but just trying to use this for AC analysis. This is really, really helpful and handy. So here, let's do this first, okay? And now so what's the first step? Do you still remember that? Get a GM, right? But however, here it's a little bit different because you do not know if the NMOS is being operated in the saturation region or not, right? So when you are calculating the GM, you are assuming it's being operated in the saturation region. It's not for now. So what you want to do is, so this time you want to do an ID first, and calculate ID first. Let's do it. IDS equals to what? Beta n over 2 BGS minus VTH n square, which is, what is beta n? Beta n is 120. From the model, you can find it per voltage square over 2 times 10 over 1. That's beta n over 2. And VGS is 2 volts minus 0.8 volts, which is the threshold voltage for the NMOS in the model. And this one equals to what? So here's 60. Let's write it down probably, which is easier for us. So that's 60 microamps per voltage square. 60 micro, so that's really 600 micro times, that's 1.2 square, which is 1.44. All right, so this will be finally, let's do a calculator. So what is that? That's 600 times something, 600 times 1.44. 600 times 1.44. All right, not too bad. 864. So that's 864. 864 microamps. Okay, so that's IDS. And if you use IDS times 5K, and you can get a DC voltage V out. So DC wise, V out So DC signal V out equals to 5 volts minus 864 microamps times 5K ohms. So what is that? If this is 900, yeah, let's don't do that. Times 5K. Times 5. And K times micro will be milli, so it's going to be 4.320 volts. So it's finally 5 volts minus 4.32 volts, which is, wait, this is too tiny. No, that's not possible. Is there anything wrong with it? That's 4,000 something times milli. Oh, that's milli. That's millivolts, right? So it's actually the voltage drop is tiny. So that's, no, that's not. So it's in linear, it's not in saturation. 500 microamps. Yeah, and one of the reasons is I'm using, I think something is wrong here. One. Yeah, I think the values I picked up will put this guy into a linear region. So that's a problem. But I think yeah, that's too much current flow through it. That's why the way to do it, you can see that the way to correct this is you can make the resistor smaller. So let's do it. Let's change it to, so now you can see that actually the resistance really affects the value. So let's make it smaller. Just do it 1K, for example. Okay. So now it's a 1K ohm resistor. It's 1K only. And that will be 5 volts minus now let's look at that. 0.8 something volts, right? So that will be 0.864 volts, and that's 4.136 volts for V out. So V out is actually VDS, right? Because V out DC wise equals to VDS, and your VGS is 2 volts, and your VDS is pretty high, and you definitely know that this is way larger than what? VGS minus VTHN, right? Which is VTHN, which is VDS set. So your NMOS is being operated in saturation. So now you can feel free just to use a GM to calculate the IDS. So GM equals to what? Beta N VGS minus VTHN, not square. And this is your beta will be 600 micro times what? Times 1.44? No, times 1.2, which is pretty close to that value. So let's see, what is that? 600 times 1.2. So actually, I can calculate it. I don't need a calculator. So that will be 720 microamps per volt, right? So that's GM. And so if you know GM, you will be able to know ID, which is GM, VGS, AC-wise VGS, right? So it's going to be 720 microamps per volt times 1 millivolt. And so you can get an AC current flow through that, which will be 720 nanoamps. Okay, and we can do a simulation for this guy, and let's check if this is accurate. So that's ID, and what about V out, AC wise? Because we know that. So let's start a new paper. So I think this is 6. Save. 6. Okay, and start a new one. Erase. Because the transistor looks like this, right? It's AC signal. And here's a resistor, and here's a ground. And your AC signal IDS or ID is going to swing around, swing in the channel to the ground like this. And that's a resistor. And you can draw a small signal model out of it. And that's a voltage. And that's a current source. We know the NMOS is a voltage control current source. And that's a resistor, 1K resistor. So plus minus VGS, and this is GM VGS. We are wondering, so what is that? I've never seen that before. All right, so we are going to use this a lot. So it's called small signal model of the NMOS transistor. So that's small signal. It's helping you to get the voltage gain out of this circuit. Because we know the NMOS transistor is a voltage control current source. So if you look at this guy here, it is a voltage control current source, right? Because it's a voltage controlled current source. That's a voltage, that's a current source. And so that's a voltage applied to the gate here as a VGS, and that's ID, right? So this is actual ID. So it's flowing in that way. This is what we considered as a positive polarity. So it's flowing in that way. And because the resistor is being shorted to the ground, so we can't directly connect to the ground. So you can imagine that if we ground over here, this is the equivalent circuit of this one, because the resistor is being connected to the ground, and here's a current source. It's going this way, right? Okay, think about it by yourself for a few moments. Make sure you understand this. So now we know. So this will be V out, right? So now we know that ID equals to 700 something. God, let me double check with that. It's 720 nanoamps. So V out AC wise equals to 720 times what? Times 1K equals to 720 microvolts. And what is the input voltage? V in AC wise, which is 1 millivolt. So V out over V in equals to 720 microvolt over 1 millivolt. So the voltage gain is actually less than 1. Okay, so the voltage gain is 720, it's actually 0.72, right? So that's the voltage gain. AC voltage gain. So it's not amplifying anything, but it's decreasing the voltage output compared to the input. All right, so we can do a quick simulation out of it. Let's do that and see if this can be verified. And you are going to work on the PMOS in the homework assignments. Let's do this quickly. I will. Yeah, I don't think I really like the drawing pad. I'm not used to it. I probably won't use it for next time. Anyway, so writing on the paper is easier, I think. So everybody is so used to that. So we are going to add a DC component and an AC component to the input voltage. So we are going to have an AC signal input. So it should be a sine wave with a DC offset, which is 2 volts, right? Remember the DC voltage to set up the operating point is 2 volts. And amplitude, let's make it, this is 1 millivolts. Assume it's a peak-to-peak voltage, which is 1 millivolts. But over here, you need to make it 2 millivolts to make a peak-to-peak voltage, to make an amplitude to be 1 millivolts. You know what I mean? Because over here, wait, let me see. Because this voltage will be the amplitude. So if you want to make 1 millivolts, you need actually 0.5. I'm sorry, 0.5 millivolts. Frequency, let's just do 1K. It doesn't matter. And let's make it 10 to 1. And let's change here to be n underscore 1u. And let's do this. And don't forget the ground for the for VDS. So the VDS is 5 volts, I remember. Okay. And I'll do a simulation. Include models.txt and do a transient analysis because it's 1K hertz. So let's do 10 of them. And there's another thing you need to know. Sometimes they will compress your figure to make your plotting looks weird. So just in case it's going to happen, I will do this. Dot option plot wing size equals to 0. This will get rid of the compression function of LT-SPICE. Will give you a normal plot. Okay, so now let's put it over here. And I think I made it visible, did I? Oh yes, over here. So let's run it. So remember what we expected from here? We expect VL to be the peak-to-peak voltage for VL to be 720 microvolts. 720 microvolts. So here's VL. Let's label VL. here. Oh, we are missing a resistor. So the resistor is 1K. Run this again and do a test over VL. So see what's the final. The 723 microvolts. This is pretty close to the calculation, and so this is verified. And if you want to see the AC current, you can also do that, but make sure you can bring up this. If you have a voltage node over here, it's hard to bring up the current meter. All right, I got it. And now let's probe it, see what the current looks like. So the current is 721 nanoamps. And based on the calculation, right, we have 720 nanoamps. This is super close. So we are getting this verified. And if you look at one of the homework, it's not, you don't have to do it today. You can do it after the Wednesday's lecture, because you can get more information from this kind of AC analysis things. So there, I put them together. So that's a PMOS version of this same problem, right? So when you are working on that, make sure you have the source on the top. So VDDs are being shorted together, and so that's VS, that's VG, right? So it's going to be VSG, which is 1.3 volts. And you're going to use this one for the PMOS. And the rest of everything is pretty similar. Just go ahead and do it. I'm going to update this figure because this one is not right, but you are going to see the correct version of this circuit. Because you can see the problem over here is I know the LT-SPICE in the model is their equivalent, right? But I didn't connect this, I didn't flip this one to the top. So actually this terminal is the source, this is the drain. So actually flip it and mirror it to make it work, okay? But anyway, I can probably run this example on Wednesday, so you'll know how to work on this. I think I'm running out of time because I was thinking I should just do a 20 minutes video, but I think I spent 10 or something minutes at the very beginning to introduce the plan for the rest of the semester. But anyway, hopefully it's already 50 something minutes. Hopefully this will be helpful for you guys for the but there's no homework assignments for this lecture, and you can start working on the homework after the Wednesday's lecture. Okay, see you later.